Murphy is a professor in department of statistics at Harvard University and also a professor of computer science. And she's a very accomplished statistician, and she's a member of the National Academy of Science and also a MacArthur fellow. Okay, so let's welcome Dr. Murphy for this talk. Okay, it's great. Can you guys in the last row hear me? I'm supposed to be using my teacher voice. It's great to be here with all of you today. I've had some really interesting discussions, and I very much appreciate that opportunity to have these discussions with people. Today I'm going to talk about, this is work in progress, and it's the lab I run is we work on how you online algorithms in mobile health, and this has to do with sequential decision making. So if you're from like applied math, think it is sort of like control, but it's not as model based as control, and you'll see some hints of that as we go through. Okay, so first I'm going to have one slide about mobile health just to get us all on the same page. So in mobile health, what happens is you have some application on your phone. It has tons of what we call intervention components, a whole bunch. And usually most of the intervention components are what's called pulls. And pulls are when you feel some need for help. Suppose you're struggling with alcoholism, mental illness, weight. You feel some need for help. You go to your phone and you access some sort of support. It may be ideas for how you can be more physically active. It could be connecting you to people who can help you, and so on. Almost all mobile apps, well, all the mobile apps I know of are mostly composed of pull components. The issue with these pull components is they force you to recognize that you need help. You have to recognize that. You have to then go to the phone and access it. But a lot of times we don't recognize when we need help, particularly if you're dealing with a chronic disorder. So pushes are something that people really want to use. So in a push, the phone interrupts you in your life while you're trying to go about your activities. And it attempts to do help you in some way. So the great thing about a push is that you don't have to recognize that you need help. You may not need to recognize that you're stressed out, you're feeling a lot of craving. Yet you might get some support, or that you've been sitting way too long at your computer and now your blood is congealed. You don't have to recognize that. The phone reaches out and tries to give you some idea how you might change your behaviors or change how you're thinking. Of course, the problem is that this thing happens as you're trying to live your life. It's incredibly aggravating. If you've ever downloaded a mobile app and you try and use it, it just can be incredibly disruptive, because you get these pings, your phone lights up, and it's completely at the wrong time. So it's pushes that really need experimentation. It's pushes that we really need to learn when and what settings and when is it best to provide a push, because of this potential for just complete aggravation. And people then delete the app, it's gone, you can't help it. So that's what we're going to talk about today, which we're going to talk about pushes. And in particular, I'm going to start off with this idea of micro-randomized trials. If you're familiar with reinforcement learning or some areas of control, this is micro-randomized trials are trials where it's complete exploration. There's no learning during the trial. In general, it gets a little bit more complicated. We're going to see that. So in these trials, each user is randomized many times. These are sequential experimentation trials. The sequential experimentation can be complete exploration, as I just mentioned, but it can also utilize a variety of online predictions to spread out interventions across the time. These are almost always constrained problems. So there's an optimization problem that's constrained, usually a probabilistic constraint, and online predictions are used to help you try and achieve that probabilistic constraint. You could also use reinforcement learning, and we're going to see an example of me doing that shortly. The second to last bullet is that there's almost always a budget, and it's usually a soft budget, a probabilistic budget, and it has to do with burden on the individual. On average, how many times do you want to interrupt the person per day or per week? The other characteristic of micro-randomized trials, which really makes them different from the field of reinforcement learning in computer science, is that you need to be able to conduct causal inference after the study's over. So these are studies that are run with people who have a variety of clinical disorders, as I mentioned, addictions, mental illness, high blood pressure, and so on, diabetes. And it takes a lot of money to run one of these studies. You have a lot of stakeholders. You need to not only discover how to help people, but you also have to advance science. And that's what we're talking about when we say causal inference. We're talking about trying to advance science, scientific understanding. So this constraint constrains everything I do. And means that in the end, I often go down a slightly different path from, say, if I was doing RL for a company. So how does the data look in these kinds of trials? Well, on each user, you get a sequence, a time series. You have at each time point, you have some amount of information that's accrued. This includes sensor data from trackers, wearables, as well as sometimes self-report, depends on the problem. A good bit of data at any rate. And then at each time, an action is chosen. This is that treatment push that should the phone or the wearable interrupt you in your life and attempt to provide an intervention. And the actions in this setting, these are behavioral treatments mainly, and they first focus on a reward that they want to accomplish. So they may want to help you become more active, or help you manage your craving, or help you manage your stress. Then they decide what the actions you might use to achieve that. So the goal is to help you in a near time, in a proximal way in your life. That's called the reward. So I'm going to talk about a particular study, a sequence of studies we're involved in. It's 3 studies where we just finished recruitment for the 3rd study. And that's the one that has algorithms running on it. The study's not finished, the recruitment is finished. It's all about here developing an activity coach for people so that they become more physically active. So there's 2 algorithms that are running in this study. One is called, we call it a sequential risk time sampling algorithm. And here, what happens is there's one of the pushes is a little message that you might get whenever you're sedentary. And it just asks you to stand up, move your arms, just move a little bit. Of course, you're not sedentary in a uniform way across the day, right? You have whole periods when you're sedentary, and you have periods when you're not sedentary. And if your budget is, say, around an average of 1.5 pushes per day, how do you spread that out across all the sedentary periods during that day? So if an oracle came down and told me, you're going to be sedentary 5 times today, and I want a budget of around 1.5 interventions per day, I would just randomize you with probably 1.5 divided by 5 at each of those times, and I'd be done with it. Of course, we don't have an oracle, and that's where the forecasting comes in that algorithm. So at each time you're sedentary, we have a prediction of how many more times during the day you're going to be sedentary. And that prediction determines the randomization probability at that time. And the goal is to spread out the budget across the sedentary times, have some sort of uniform across all sedentary times. So that's running, but I'm not going to focus on that algorithm. It turns out that algorithm is working just gloriously in this trial. I'm going to focus on the second algorithm, which is not working so gloriously. It's one of the reasons why I wanted to talk about it. So this is where we're using a reinforcement learning algorithm. And here we have a binary action. Should we send you, I'll show you an example. It's it's a message that a little message you can, to help you be more active, physically active in the moment, versus no message at all. And the goal is to maximize, rewards here is physical activity, is to maximize your physical activity over the 3-month study. So let's get to that reinforcement learning, build up to it. So what's the action here? What happens is your phone pings audibly, it lights up, and on the face of the phone, you get a little notification. And the content of the notification is tailored to your current location. It's tailored to the sensor data we're getting at that time. And these individuals are wearing a tracker, and then we have sensors on the phone as well. So it's tailored to the weather outside, whether you're at home or work, whether it's a weekday and a weekend, and something else too, which I can't remember right now. So this message, hopefully you can see it. This arrived, this was another, I got this message in Michigan, when I was still in Michigan. It was very cold outside. It was in the morning on a work day. And you can see the kind of message I got. Hey, look outside, it's not so bad. Of course, it was really bad, but it's trying to help me reframe things. Maybe you should just walk or park a little bit further away. And how does, these messages can appear at any of 5 times a day, and the 5 times are related to your work schedule. So if Brian and I were in this intervention, his times might be very different from my times, because it's related to how our work, when we go to work, when we leave work, and so on. And the reward is how physically active I am, that user is in the subsequent 30 minutes. So some of those times the user will get a message, sometimes they're not. It's a little more complicated than that, but that's the general idea. Sometimes they get a message, sometimes they don't, and then you look at their physical activity in the subsequent 30 minutes. And from that, you want to learn, was it worthwhile to send that message to that individual in that particular context at that time?
Do people carry a monitoring device? I mean,
excuse me?
Do people carry some device that monitors their stuff?
Yeah, so in this study, people have a tracker. It's a commercial tracker, and we have an app on the phone. And so the engineering aspect of this is pretty complicated, because the way in which the tracker communicates with the cloud is complicated. You get out of wireless access. So there's all these ancillary issues that go on when you design something, because the engineering of the system itself is complicated to ensure that it's stable and you have an accurate context inference at that time. But that's not, I'm going to gloss over all of that. But they are wearing a tracker on their wrist. We do have step count on the phone, but that's known to be pretty poor. So I'm going to talk about some of the challenges to reinforcement learning in this kind of setting. So again, we're talking about sequential decisions. This was the first study was 42 days. The study we're right in the middle of is a 90-day study. At each of 5 times per day, you may or may not get a suggestion, and we want to learn as the study progresses whether or not it's worthwhile to give you a suggestion. If we do, we give it to you with greater chance, right? That's the idea somehow. So these algorithms are online algorithms, at least the way I'm going to discuss it here. We are doing online algorithms. And the goal is to select your actions to maximize the rewards over some horizon, some finite horizon. The horizon here is H. And you might say, well, Susan, we know in Markov decision processes, most everybody uses discounted horizon. But here, the real issue in this setting is that you may get someone to be a little bit more active in the moment, but the delayed effects are probably that they get tired of being interrupted and they stop responding. So I really want to pay attention. I want to weigh the later times in that horizon equally with the earlier times in the horizon, because of this paramount concern that the user will get tired of this whole app and delete the app. So that's why you don't see a discounted horizon problem here, you see a finite horizon problem. And the reward is just the expectation of the reward, in our case 30-minute step count, given the context of the action, some function, which you don't know.
So is the horizon fixed?
Yeah, the horizon comes out, I don't see who
Yes.
asked. Yeah, the horizon comes out of the science. So right now, what we're in this particular problem, we're going to have a horizon. You'll see it's we're going to be using something akin to a bandit. So the horizon is 1. But in general, the horizon, for example, I can tell you later, but what we see is that people start to habituate and disengage around 3 weeks in if you're intervening at this rate. So a natural horizon would be around 21 days or so that you pick up that delayed effect. Yeah, so the horizon comes from the domain. It doesn't, it's not a tuning parameter. It's not part of my learning algorithm. So how does RL attempt to maximize the sum of the rewards? So I'm going to communicate to you as a statistician. I don't think I understood this when I first started reading in this literature. But once you realize that it's obvious from then on, is all RL algorithms have they're actually 2 algorithms, and they're put together. And any RL algorithm is a mix, and you match 2 different algorithms together. So you'll see tons and tons, they all have different names, but you've got to identify these 2 underpinning algorithms, how they mixed and matched them. The first algorithm is some sort of learning algorithm. That is, you're trying to incrementally estimate a model. And the second, and then as you go along, you're updating that model. And the second algorithm is an experimentation strategy. And it depends on the algorithm, whether or not that has randomization in it. It might not be, it might not, but it's still, there is an experimentation strategy in every online RL algorithm. And somehow that experimentation strategy uses the information from the learning algorithm to do the experimentation, somehow or another. And again, people mix and match the 2 all the time. So what are some of the challenges? So when I think about what should my learning algorithm be, what should my experimentation strategy be, what are some of the challenges? Well, this is a setting where you're experimenting in real life, right? In the life of these people. As they go to the grocery store, as they go to work, as they go in meetings, as they come to a talk like this, and so on. So the noise level it's a highly noisy environment. And if you learn slowly, your user disengages. You have a short time to make a difference. And if you overtreat, they're gone. And if you've ever downloaded an app from the App Store, you'll know exactly what I'm talking about. And also, I mentioned this, the second bullet point, I mentioned this earlier, there's a variety. So this is not a wellness app. We're not talking about wellness. So we don't have 100,000, 1 million users. This is an app that's being developed for a more clinical population. And thus you have all these stakeholders that want to advance the science, the underlying science. So again, that whole issue, we've got to be able to conduct causal inferences after the study is over. And in general, if you were going to roll this out, you'd want to be able to conduct inferences at regular intervals to monitor the app, to monitor the algorithm. The next challenge, the third challenge, there's a lot of challenges, but these are the 3 I want to focus on today, is that, and I mentioned this already, the treatment actions tend to have a positive impact on the immediate rewards. That is, if I send you a message about how you might walk to the furthest restroom or walk up to the top floor, that's more likely, you're probably going to have more physical activity than if I don't bother you at all, right? So you tend to have a positive impact, if any kind, positive or 0 impact on near-time physical activity. But in the delayed effects, you would hope that people would get new habits and have this increased repertoire of things they can do. But that's very low signal. The big signal in the delayed effects is people get overburdened and they start ignoring every time you interrupt. Either they don't overburden or they habituate. They're very different things. Habituation is when I send you a signal repeatedly. After a while, you don't even see the signal. You may be totally engaged. You may want to be physically active. You just don't see the signal anymore. That's habituation. So in both these cases, we want to manage this. And you asked me about horizon, and I just said in this study the horizon is 1. So right away you know I got to do something, because with a horizon of 1, I am definitely not managing delayed effects.
There's something I don't understand with your horizon, because you're not, I mean, when you wrote your formula, it was always taking the reward conditional to the immediate past, even with a non-horizon application one. Is it equivalent to, I mean, you would have expected that you would take the solution at time t and then compute the conditional expectation of the reward at time t plus k.
Right.
With k between 0 and h, but this is not
No, so this is, if I go for horizon, if in this study we started with a horizon of 1, and I'll explain why. At first, in general, it's going to be a longer horizon, but then my goal is, if that's the case, is to figure out what action to take at this moment to increase the physical activity in the next 30 minutes. That's it. So I know my context. I can calculate my expected 30-minute step count, the reward, given my current state, current action, current context, current action, and I want to get the argmax. I mean, essentially, if you knew what that expectation is, the oracle. So what you're comparing to is an oracle. And the oracle would just knows the reward function and uses the action, which is the argmax. Now, if you have a finite horizon, more than 1, then the oracle wants to get the maximal. It wants a policy, a finite horizon policy, which is a sequence of decision rules, 1 per horizon, 1 per step in the horizon. The one thing the horizon is not is the duration of the trial. The duration of the trial is is a separate thing. So I'm gonna try and come back to this. Don't let me forget. So the whole purpose of these studies, they were funded to develop an app that would help people who are at high risk of adverse cardiac events. And what I'm going to do is I'm going to report on the results of the first study, because that sets us up for the study that's in the field that has the algorithms run. Okay, so the first study was like I said, it was a 6-week study, and it showed phenomenal results. The tailored activity suggestion, I showed you an example on a prior slide, as compared to no activity suggestion, regardless of current context, and averaged over current context, initially increased step count by 271 steps. These are very sedentary people. They get around 250 steps in a 30-minute window around these times. This is more than doubling their physical activity. I mean, this is a profound impact on physical activity. But by 3 weeks in, it was over. It had no impact on people. And the general thought through a lot of other analyses is that it was habituation. People no longer even noticed that the phone lighted up anymore. They didn't even see the messages. And so they just habituated. So this is really concerning, because now you start to think, how do you run? Remember, that third study is like 9 months long. I can't have a setting where 3 weeks in, everything's over. We can't have an algorithm running where 3 weeks in, everything's over, right? It's just, that's not going to be helpful. So this is exactly the setting where you might think reinforcement learning would help you. Because a good reinforcement learning algorithm will back off when there's less, in context in which there's less evidence of an effect, and increase when there's more evidence of an effect. It would allow dishabituation. Okay. So I just want to, so these are the variables that are going to be, not the time in study, the prior message dose, current location, how variable your step count was over the prior 7 days in that same hour window around that time. All of these impacted how responsive people were, at least from the study, the analyses we saw. So they're going to enter into any kind of decision rule that we're thinking of. It's not very many variables, but they do have a lot of values. Okay, so I'm just being a little repetitive so that I'm clear. So what we're going to do is these results motivate us to use a reinforcement learning to do the micro-randomization. I.e., that is to sequentially experiment with this binary treatment action so as to maximize the sum of rewards here. So again, 5 time points per day, and the reward is a 30-minute step count subsequent to each time.
So was the 5 times per day decided by the policy, or it's predetermined by the user?
It's predetermined by the user, and it can change at any given time, and it can be different on weekends and weekdays.
So then how did you control for the exploitation, where the algorithm will pick the time that the user is most likely to be active and it keep pushing?
Yeah, so this algorithm doesn't learn, it only will learn if at one of those times, in a particular context, if it's useful. It won't learn, for example, that at a time that's not one of these 5 times, it's useful to send a message. It won't learn that because it's not exploring that at all. And the reason, so I'll backtrack if you heard my talk yesterday. The reason why we're doing that is when we first started, we were going to have decision times every minute during the day because we were thinking like you're thinking, you know, at any given minute, it might be useful to send a message so the person could be more physically active. Then we got access to a large amount of tracker data, the commercial tracker was used here. And the within-person variance in their physical activity was highest related to their work schedule. So there's times in your day where you have almost no variance in your physical activity. That indicates that it's probably unlikely that we can impact you. Whereas if you have a lot of high within-person variance in your physical activity at a particular time, that means that's a time that you might be much more open to increasing your activity because you have a lot of variance. Sometimes you're really active, sometimes you're not. So that's why we chose those 5 times. It came from prior data. So this is all, it's very much incremental research, right? And that's probably why we got such great results in that first study. We didn't do the minute by minute thing. In other studies, we are doing minute by minute. It's just not in this one. Okay. So I'm going to give you an algorithm. So I'm going to start off with what's called a bandit. We in statistics invented this algorithm a long time ago. And then we all walked off. And the computer scientists took over and went places with it. It's quite a travesty. So, just by the way. Anyway, so here's the vanilla version, and then we're going to make it more and more focused on our setting, the setting that we care about. So the item here is a banded algorithm. Automatically, you should think, oh, she's focusing on horizon h = 1 when I say that, okay? So you have some model for the mean reward given context S and action A. The algorithm proceeds in time, at each decision time. You observe context features, so you know the context, whatever context you have. I gave you some of those contextual variables on a prior slide. Then your experimentation strategy selects the treatment. Then you observe the reward, so this is happening in real time. Then the learning algorithm updates the parameters in your model for the reward, or the distribution of the reward. And then you go to the next time point, and you just proceed on through time. That's essentially what the algorithm is doing. So we're going to, our base algorithm is going to be a Thompson sampling algorithm. So a linear, so here we have a linear model for the mean reward. Now if you have a lot of data, you can have features. That feature vector F can be very high dimensional, right? It can be a basis function type setting. Ours won't be because we won't have as much data. We'll trade bias and variance. And what we'll do is we'll initialize the coefficients of those features. F is a feature of context and action. We'll initialize that using a prior distribution. And that prior distribution I'll talk about later, but we only use informative priors. We don't use uninformative priors. And we'll use a Gaussian. And then, so in step 4, which is the learning algorithm part, we update the posterior of these coefficients, the etas, given the next context, action, and reward. And the posterior, if we're in a total Gaussian world, it's all explicit. We, you get a posterior, the Gaussian is posterior. And then what we do is we use posterior sampling. So our experimentation strategy is called posterior sampling. And what it does is it selects the next treatment, say, send a message, with the posterior probability that sending a message will result in a higher reward than not sending a message. So to summarize, the learning algorithm is a Bayesian linear regression model, also called a Gaussian process model. The experimentation strategy is posterior sampling, and in our case, it's just, you see the blue line. Select, send a message using the posterior probability that the reward in that particular context that you're in, under action 1, is higher than under action 0. So I just want to, if you're not familiar with this field, I put this slide because I think this is really important, and it takes a while to realize this fact. Okay, the Thompson sampling bandit is just an approximation to learning the best action for a given context. And in particular, the posterior probability, using posterior probabilities to select your action, does not optimize exploration. It doesn't balance exploration with exploitation. If you wanted to do that in this setting, what you would do is you'd have to roll out the posterior distribution of the reward into the future under all sequences of action selections, and then use dynamic programming to move backwards in time. And you'd end up with a deterministic decision, choosing action A for 1 or 0. That balances exploration and exploitation. Posterior sampling is like a poor man's alternative to that. It replaces that rollout with the use of a posterior probability. And it turns out this is a great algorithm. It's being used all across in business to service ads when we go to our websites, Facebook, and so on. This type of algorithm is being used. And it achieves maximizing the total rewards over the entire study. It achieves an optimal rate of doing that, the study duration. So for people who realize, I just want to, I think people, when you don't know the model, and so you're doing a bandit, so your horizon is 1, you don't know the model, so all of a sudden you end up being in something akin to a Markov decision process with a horizon of the study. It's very interesting. Okay, so let's go to these challenges for mobile health and see how this vanilla algorithm